Right. Good morning, everyone, and thank you for joining our webinar titled Uncovering the Unseen, where we will be discussing event detection through computer vision. It's an incredibly exciting topic, and I am very excited to be taking you through it and sharing it with you. Before we begin, just some housekeeping rules. Please ensure your microphone is on mute for the duration of the webinar. This webinar will be recorded and the recording will be made available to you via social media. And finally, we love hearing your feedback. We love hearing your questions. We would love to answer them. So please, throughout the duration of the webinar, pop your questions in the chat and we will get to them and we'll cover them in the question and answer session at the end of the session. We love hearing from you. Any comments that you may have, any feedback that you may have, or any questions that you may have, you can pop us a message and we will address them at the end of the webinar. Just a bit about myself. My name is Doron Jaffe. I am a software consultant at Opti-Num Solutions. I work primarily in the mining and manufacturing spaces. We develop computer vision algorithms for mining and manufacturing use cases, as well as data-driven solutions for mining and manufacturing clients. My background is in chemical engineering, and my email address is on the screen, so you can pop me an email if you have any comments or questions. Right, just a bit about Opti-Num Solutions. We are a strategy and technical consulting company, and we are experts in MATLAB and Simulink. We partner with our clients to develop data-driven solutions to complex problems. We're actually the sole authorized reseller of MathWorks products in South Africa, and you'll recognize some of our clients. They include the likes of MTN, Nedbank, Anglo American, CSIR, Sasol, and Hensoldt. As you'll notice, our clients and the work we do spans many different industries, including business analytics, financial engineering, mining and manufacturing, which is where I work, digital engineering, as well as the education space, servicing our universities across South Africa. Right, we've got a jam-packed, exciting schedule for this morning. We are going to have a look at an overview, a brief overview of computer vision. We'll have a look at quite an exciting and up-and-coming, often talked about topic called virtual fencing. And we'll look at virtual fences for mining and manufacturing. We'll have a look at a live MATLAB demo of a virtual fence. We'll then have a look at some dangerous condition detection using object detection and computer vision algorithms. And we'll have a look at a second MATLAB demo where we will detect dangerous conditions using smoke detection with computer vision. So a lot to talk about, some exciting topics. Let's jump straight into it. Let's have a look at a brief overview of computer vision algorithms and some of the common applications. The first often used application is what we call anomaly detection. And my colleague Virushan Kupu delivered a webinar on anomaly detection a couple of weeks ago. The link to that webinar will be posted in the chat, so you can check out all the details on that. But to break it down, anomaly detection, we train an algorithm to detect an anomalous situation in a particular image. So this particular example is a screenshot from a thermal camera, and the algorithm would output a signal of perhaps abnormal if it will detect this image as perhaps slightly too red or slightly too green, indicating that the temperature is slightly low or slightly high. We train this anomaly detector algorithm on normal images, so it learns what normal is, and then by default, everything that is not normal will be flagged as being anomalous. The next common use case is object detection and tracking. We want to know what is in a particular image. In this case, we are detecting operators on a construction site. We want to know where those operators are. Are they working in a dangerous zone? We might want to detect, let's say, a hard hat or a piece of PPE equipment to ensure that our workers are complying to safety protocols. And then finally, another common application is process automation. So getting a computer vision algorithm to, let's say, count parts on a conveyor belt or inspect the quality of those parts on the conveyor belt. Now, many of these tasks could be conducted by human beings, but having a computer vision algorithm do it for us obviously saves time. We don't need to have operators performing these laborious tasks such as counting objects, and there are safety implications as well. Instead of having a human go down a mine to ensure someone is wearing PPE equipment, we could have a camera and we could link that up to a computer vision algorithm, and we save on having to have a person there and the safety implications or the safety hazards that that can cause. Now, these are just but a few applications, and my challenge to you is throughout this webinar, I want you to think, where can you deploy a computer vision workflow, computer vision algorithm in your business use case? And the applications are incredibly diverse. They're endless, whether you're in a mining or manufacturing environment where the application is fairly obvious. And even if you're in, let's say, a corporate world, a bank, and you want to, let's say, optimize your security camera systems with a computer vision algorithm. The applications are endless, and my challenge to you is to think, where can a computer vision algorithm apply to your business use case? Let's have a look at a brief overview of some different types of computer vision algorithm. A simple type of algorithm is what we call image classification. We get our computer to tell us what is in the image. Does this image contain a dog? Yes or no? Very simple. Is this a dog? Yes or no? A slightly more complex type of application is what we call object detection, where we get the computer to tell us, is there a dog in the image? But we also ask the computer to tell us where in that image the dog is. That's called object localization. So it's slightly more specialized. We're detecting the dog, and we want to detect where in the image that dog is. And then finally, one of the most specialized types of computer vision algorithms is what we call image segmentation. And that is where we detect on a pixel level, does this pixel belong to a dog, yes or no? When would we use these different applications? So my colleagues and I recently had the privilege to work on a medical imaging project, and we have to segment regions of the body. So if we want to, let's say, segment the femur bone, we want to get the exact contours of that femur bone. We don't want soft tissue to come along with it. So we would use that final application, image segmentation, where we trace the contours. Whereas if we just want to detect whether the dog is in the image and where the dog is, we don't need to get the exact contours and shape of the dog's body. So that is a brief overview of the different types of computer vision algorithms that we have, and obviously there are a lot more. These are just an example of 3. Today in this webinar, we are going to focus on object detection. So detecting where objects are in a particular image. Let's have a look at our first example, and this is the idea of virtual fencing, and many people are talking about this. It's a very useful and very interesting use case. Essentially, what we do is we draw a region around a particular area. It could be a dangerous area, it could be an area which we want to section off, and we will detect whether an object has passed into that region, whether an object has breached that virtual fence, or if an object has left that virtual fence. And of course, the obvious application would be for security. We can have a virtual fence around a house, and we can detect intruders. Or in a mining and manufacturing space, we could have a virtual fence around a hazardous zone, and we can warn the control room if an operator or if a piece of equipment has entered into that zone, like we have over here. Let's have a look at how we are going to do this. We're going to use what's called a neural network. And a neural network is just a tool for us to detect these objects. And I want to emphasize a very, very important point. Very often people hear the terms artificial intelligence, computer vision, deep learning, machine learning, and there's a lot of mystery surrounding these concepts. People often think, well, that's for the experienced people. How can I possibly implement such an algorithm in my use case? We need hours and hours of knowledge of these particular concepts. And I hope to demonstrate that that is not true, that we can use a very simple workflow and we can actually deploy an end-to-end algorithm, an entire computer vision algorithm in just a few lines of code. And the way we're going to do this is we are going to use a pre-trained network. So this network was trained by someone on millions and millions of images using incredibly powerful computers. And they trained that network to detect certain objects, let's say people, tables, dogs, and cats. And we can use that network as is, and we can apply it to our application. Because remember, what do we want to do? We are going to draw a virtual fence. We are going to detect people in a particular image. And once we've detected those people, we are going to determine whether they have entered our virtual fence or our zone that we have defined. Which means if we can find a network that exists already that detects people, we can use it. We don't need any additional training data. We don't need to do any training, and we don't need to have any knowledge of this complex infrastructure over here, because you can imagine the mathematics behind a deep learning network is quite complex. We need to have no knowledge of that. And we're going to do a demonstration, a live demonstration, how we implement this in MATLAB. Before we begin, let's just have a look at the computer vision architecture. We're going to start with a camera. So we need a stream from a CCTV camera, which a manufacturing plant or a mine or any other business would have on there in their environment. This particular image or this particular camera, which we're going to stream from in our demonstration, is covering this construction zone. You can see there's a few workers, there's a piece of machinery, and this machine is operating in quite a dangerous environment. It looks like some form of landslide or something like that. And we want to warn the control room if someone enters that zone. Once we have acquired an image from our camera, we are going to pass it to our pre-trained network. Again, we're not going to do anything to our network. We're going to use it as is. But now, and this is very, very important, we need to do something with that detection. It's all very well doing all these fancy computer vision detections, but we need to actually log that data somewhere. Typically in a mining and manufacturing space, there will be a central control room, which would have some form of a PLC or SCADA system, and we will use an OPC server, which is just a data exchange server, to log that data to the control room. And then the operators might want to see what that network or what our algorithm has been detecting. So we want to stream our output to the control room as well. And the reason for that is perhaps the operators want to rewind and see what happened in the past. We need to stream our video footage, our process video footage, to the control room. And this is the infrastructure that we are going to build. One last slide before we jump into our MATLAB demonstration. Let's just have a look at the type of network that we are going to be using in this particular demonstration. We're going to be using a network called a YOLO network. And YOLO stands for you only look once. So historically, what used to happen with these neural networks is they used to look for a particular class. So in this example, the network would scan the image and it would find the car in the image. Once it's located the car in the image, it would then go back and look for the person. Then it would look for the robot. And you can imagine that would be quite a time-intensive process. Whereas you only look once networks scan that image in one shot, and it finds all the classes in one shot. And that is very useful when speed is of the essence, which is typically the case in these computer vision algorithms. So let's, without any further ado, we've got all the background, we know what we're going to do. Let's jump into our first MATLAB demonstration. Okay, so I'm going to come over here to my MATLAB live script, which is a very useful tool which MATLAB has for these types of demonstrations. Now, again, let's just drive home the workflow, what we're trying to achieve. We're going to load a pre-trained network. We are going to instantiate an OPC object so that we can stream and log our data to some form of OPC or SCADA system. We are going to create a video stream to connect to a camera. We are then going to create the virtual fence, and we're then going to detect fence breaches, whether someone has entered or breached that fence. Over here, I can load in my detector, and I'm using this. This is the name of my detector, and I just want to open this up so I can drive my point home why we can use this. Over here, I've got the actual network, which is where all the fancy mathematics takes place. And let's have a look at the class names of this particular network. This network has been trained on 80 different classes. So this network can detect people, bicycles, cars, all the way down to quite random objects such as a pot plant, a bed, dining room table. Now, all of these things are totally irrelevant to me. But because this network can detect people, I can use it. Because if my if my image has got a person in it, my network will be able to detect it, and I don't really care about the 79 other classes that this network has been trained on. Again, I haven't done any work, I've just loaded in a pre-trained network. I'm not going to go through the detailed code. This live script will be made available to you, and you can have a look at it. What I do is I instantiate an OPC object. I am using the KEP Server X version 6 for my OPC server for this demonstration. I can connect to a video stream using a very simple function, the IP-cam function, and all you need is your camera's URL, and you can tap into that particular video stream. I'm going to have a look at my virtual fence function, and it sounds fancy, but it's literally just one line, the draw polygon function. You can't get a more intuitive name than that. If I open that up, it allows me to just draw points in space, because a virtual fence is essentially just a polygon. And of course, this would be an image in the background, and I've drawn and created my virtual fence. Once I've done that, you can use the detect function, and then you can check the fence breach. Again, this will be made available, and you can have a look at the nitty-gritties of this code. And then we can use the write async function to log our data to an OPC system. Let's have a look at a live demonstration of this. We do have a very neat application. And in this application, we are just going to follow those exact same steps. I'm going to take a snapshot from my camera, and you can see we are linking to this camera. Obviously, in this particular webinar, this isn't live, but the idea is that we would do this live. Okay, we link to some form of an image, then we're going to create our virtual fence, and we have this very neat application for our clients, which makes this concept very, very intuitive and very, very user-friendly. We are going to draw a polygon. And again, I want to draw a virtual fence around this particular danger zone over here. Okay, let's put it somewhere over here. And when you're doing this, you would get your exact contours correct. Once that has been drawn, we can apply. Okay, I'm going to connect to my OPC server. And over here, this is what my OPC server looks like. I've got two tags on the server. I've got the fence access breach tag, and this will toggle between a 0 and a 1, depending on whether that fence has been breached. And I've got my people count tag. And when I begin the video, I want you to look at the interaction between the algorithm and this OPC server. Of course, what's taking place is we are making those human detections, those people detections, and we are detecting whether that fence has been breached. What you see in the video, you see our fence, we see our 3 humans, and you see that 3 value, the fence has been breached. That value turns to a 1. That person's going to move off the screen, so that value should turn to a 2. It's going to come back on, turns to a 3. We get another person in the top right corner, that changes to a 4. Now, I'm not sure about you, but I can watch that over and over again. So let's just do it one more time. And again, focus on the interaction between our server and our video analytics. Very, very exciting. Right. Now, the operators may want to see exactly what's going on. So we want to stream our output with those overlaid boxes to the control room. Now, very often at Opti-Num Solutions, we get asked the question, why don't you use C++? Why don't you use Python? Why are you using MATLAB? And I always say to them, well, why don't we try and use both? MATLAB has got some very powerful capabilities to integrate other software languages within the actual MATLAB environment. So C++ has got some very cool and powerful streaming functionality. So we can use and leverage the C++ streaming functionality and bring it into a MATLAB workflow. Over here, I have got a C++ function, and this C++ function controls that streaming by opening a streaming pipeline over here. I've put in my streaming parameters, such as my frame rate, the video sizes. I'm using FFmpeg, which is a streaming software, and I can specify the destination, the RTSP server. RTSP is just a streaming protocol. Similar to HTTP, we've got an RTSP protocol to facilitate that streaming. So I'm using a C++ code within my MATLAB workflow. This is very, very cool. Very, very exciting. The idea of a virtual fence using computer vision. All right, let's hop back into our presentation. Okay, we had a look at our YOLO network. Now, you may be sitting there and wondering to yourself, okay, that's very good. What happens if I have got an image which has an object which is not included in that list of 80 that that network can detect? Well, what happens if it is? But what happens if, let's say, I've got people in my image which don't look like typical people? We had a client a couple of months ago who came to us and asked us to implement a virtual fence, and I was very excited. I was like, perfect, we can have a fully functional workflow within 20 minutes. I had a look at their images, at their video stream, and they had operators on a particular mine, and they were fully clouded in PPE. They were wearing fire retardant silver outfits, and I put the images through the network, and we made 1 out of 50 detections because the people didn't look like the people which this network would have trained on. So what are we going to do then? We can't just use a pre-trained network. So that brings us to our next topic, which is called transfer learning. And this is when we take a pre-trained network and we modify that network for our particular use case, because this network has still got very powerful capabilities in the back end. It's got an ability to extract features from an image and analyze those features. So we can use and leverage that powerful capability, and we can modify it slightly and retrain that network to identify the particular class that we wanted to identify. In this example, we are going to look at a dangerous situation where smoke is produced. Okay, so we had a client who came to us. The client had a particular piece of machinery, and a leading indicator of a machine fault was smoke being produced from this particular piece of equipment. And obviously, you would think that an operator would be able to locate that smoke and raise an alarm, but this cloud of smoke would last only a couple of seconds, and then there would be no symptoms that anything was wrong. So very often an operator would miss it. And the idea was that we would tap into their camera system, we would do video analytics on that camera feed, and we would be able to object detect the smoke in a particular image. Obviously, we would follow our computer vision workflow. We would log our data through OPC to their PLC and SCADA system, so they could do all their visualizations, they could raise an alarm if necessary, and we would stream our output through a video streaming server. Again, just to emphasize, the reason why we want to stream our output is perhaps the operators want to rewind. We might have raised an alarm, and now that cloud of smoke has disappeared, and the operators are going to think, well, why is the alarm going off? There's no smoke in the video. Then they would be able to rewind and see historically, well, there was a cloud of smoke that was detected. So that's why this RTSP streaming protocol, this RTSP streaming infrastructure is of particular importance. All right, let's jump over into our MATLAB demonstration. Okay. Again, let's just emphasize our workflow, what we want to achieve. in this particular workflow, we need to configure a new data set because we need to retrain our YOLO v4 network because smoke was definitely not one of the classes which our pre-trained network was trained to detect. Once we have done that, we can create our object detector. Now, again, we often get asked, what capabilities does MATLAB have over the more conventional software such as Python? Now, when it comes to training these networks, MATLAB has got incredibly powerful techniques or applications because very often we see these cool computer vision algorithms. Our algorithms are detecting all types of things, but you always need to think there was some guy in the background who had to sit there and manually label that data. Some person had to sit there and draw boxes around the particular classes in an image to train our network. And that can be an incredibly laborious task. But MATLAB has got a very powerful capability to semi-automate that process. And let's have a look at what that workflow looks like. I'm going to go to my application tab over here, and I'm going to open the video labeling application. And what this allows me to do is it allows me to load in a video and allows me to generate training labels. So I have done that already. Over here, what I've done is I've loaded in a video of a forest fire. Why a forest fire? Because again, we want to detect smoke in a particular image, and a forest fire would typically have a lot of smoke in it. I create my label over here, and now what I can do is I can go and physically manually label this. But of course, that would take me a long time to do. Draw these boxes around all these images within my video. So what I'm going to do is I'm going to semi-automate this task. And I want to spend a bit of time discussing it because this is a very important point, but it can be quite subtle. What I can do is I can manually label, let's say, 50 images, and I can train a network. Now, that network will not be accurate at all. Why? Because these networks typically take many, many images to be an accurate network, let's say northwards of 500. I can do it on 50 and train a network. It will not be accurate. But I can take that inaccurate network and I can use that inaccurate network to generate additional labels on a new training data. And now I've got a data set of more labels and more images, and I can train a network. That second network might also not be particularly accurate because it also hasn't seen that many images. But then I can take that second network and I can use it again to generate more labels on more images. And then I can take that full data set and train a final network which will be accurate because it has a lot of labels and a lot of images to train on. So again, we are going to use an inaccurate network to generate additional training data for me. Let's have a look at what that looks like. So I have loaded in a network in the background in settings over here. So I've got a smoke labeling automation function. And essentially what that is, it's just a badly trained network, which is going to generate bounding boxes for me. And this will severely cut down on time, on training time. Okay, let me open that up again. I'm going to click run and notice how my network, without me doing anything, is generating labels for me. They're not 100% accurate because, again, this is an inaccurate network, but I'm going to use these labels now to train a better network. Okay, once this is complete, I can accept it. And now I can go back and I can slightly adjust it. I might want to lift this up slightly, like that. Okay, I could go to the end. Okay, I might not like this label that my network generated for me, so I can just delete it. And I can perhaps drop this down slightly. And again, I'll just need to make slight adjustments to it, which would drastically cut down on my training time. Once I've done that, I can export this to my workspace. And this comes out as a ground truth object. Okay, let's have a look at what that looks like. It's essentially just an object which holds the labeled the data. These are the coordinates of those boxes that were drawn. A very powerful tool for data labeling. Now, my colleague Virushan Kupu, in his webinar, he covered the detailed training process for training these networks. You can have a look at that. I'm not going to touch on the entire workflow. You can have a look at that in his webinar. I just want to touch on one more point, and that is the data augmentation point. This is a very interesting tool. We have generated images, or we have trained this network on images from a particular video, but the external surroundings in that video might be different to the surroundings in my particular application. So the sky might have been dark because it was a rainy day in that training data, whereas I might have, let's say, a sunny day in Johannesburg, and then my network's going to be confused. So I can slightly augment my data to account for those variations. So what I've done here in the top right corner, you can see the original image. It was that those three panels. Over here in the top left corner, I've jittered those colors slightly to account for slight variations in my environment so that my network doesn't overfit, so that my network doesn't train on a particular type of image, and then it won't generalize to my particular use case. Bottom right corner, I've just changed and altered those colors slightly more, and the same with the bottom left corner. I can do all types of augmentations. We can rotate the images, we can flip them up and down. We might have, let's say, a person in my training data wearing a red hat, and then my network will be confused if he's wearing a slightly darker red hat. And therefore, I want to jitter my colors slightly to train a network. But again, the actual details of training these networks have been covered in the previous webinar. Once I have got my training data, I can train my network. Again, this is that same detector, that pre-trained network. So I'm still leveraging the power of a pre-trained network, but I'm passing it this augmented training data so that I can modify it to my use case. And then you can train this network with these training options. Excellent. Let's pop back into the presentation. Okay, of course, we've looked at training that smoke detection network, and the same steps would apply to instantiate our OPC server and then stream our output to some form of video streaming server. Right. That brings me to the end of the content for this webinar. Let's just have a quick recap as to what we have discussed. We looked at some applications of computer vision. We looked at a brief overview of anomaly detection, as well as our object detection and then process automation. We had a look at a very exciting in my opinion, concept of virtual fences, which can cut down on resources. We don't need to have acres and acres of fencing, so that cut down on costs. It was a very effective way to monitor people in dangerous environments, such as a mining and manufacturing space. Just a very useful concept in general. We had a look at what was called dangerous condition detection. There we had to modify our network slightly to detect smoke and adapt that deep learning network to our particular use case. And then we looked at some of the infrastructure surrounding these computer vision algorithms. Again, it's no use making all these fancy detections and doing all these powerful things if we can't do something useful with that information. And therefore, we have to have an infrastructure in place to stream our output or log our data to a control room, or stream our video output to a control room for the operators to download that output. They could write up a report based on that historical video footage. And again, I hope I've demonstrated the ease at which these applications can be implemented. We can take away some of the mystery which surrounds artificial intelligence. Now, don't get me wrong. These can be very, very complex to build up these networks and tailor make them for a particular application. But at least to get started, we can implement an end-to-end workflow in but a couple of lines of code. And I hope that point comes out. Right. Do you have any data? We'd love to get in touch with you. You could pop me an email. My email address is on the slide. And again, just to emphasize, people don't know that they've got data. If you have got a CCTV camera, you're already sitting on a minefield of hundreds and hundreds of hours of video. And a computer vision application can be implemented in any use case, whether you're a mining and manufacturing customer, whether you're in the corporate world, a bank who wants to optimize their CCTV footage, security footage, optimize their parking spaces, for example. The possibilities are endless. Just want to remind you of our upcoming webinar. This will be presented by my colleague, Enzo Duplessis. It'll be on the 13th of September. He will be discussing real-world applications of condition monitoring through thermal cameras. Again, a real-life use case of computer vision algorithms in a mining and manufacturing space and in industry in general. All right. Any questions? We would love to hear your feedback. Any comments? You can unmute your microphones. You can post a comment or a question in the chat. We'd love to hear from you. Alternatively, you can pop me an email and we can engage over email or on LinkedIn. There's a question, a hand up. Yes. D or Mazia, you've got a question?
Yes. Good day, everyone. Good day, Mr. Doran. Thanks for this webinar. I really appreciate what you have already presented. My question is that because I'm interested in safety purposes. Yeah, I'm working for ESCOM in one of the power station, Machuba power station. So I just want to know if it's possible to design or train a data that can detect, especially in our work condition, because we are, and most of the time we have a lot of incidents or accident concerning falling objects. Can we design something like that can detect in advance that there might be a falling object where our people are working and action be taken before it happens? Thank you.
So thank you for that question. It's a very interesting question, quite an interesting use case. And I'm just thinking off the top of my head what we could possibly do. We could implement an algorithm to look at the stability of a stockpile, for example. So if an object is leaning at a particular dangerous angle, we would be able to detect that that object might be able to fall or might fall. So we would have a look at a particular image. We would pass that into an algorithm. If the algorithm detects that the image or a particular object is loosely connected to something, for example, it would raise a flag. If it's at a weird angle, it would be able to raise a flag. So most definitely, that could be a very nice use case of this. We would detect certain properties of the position of that object, whether it's the angle, whether it's the this, whether it's safely secured. We would be able to detect that, and we would be able to determine whether that would pose a hazard. That would be a perfect example of computer vision for safety.
Yes, especially when they are doing rigging, because a lot of accidents are happening when rigging is taking place. You might find that maybe whatever they are rigging with, it snaps, and you find the object falling on top of someone and getting crushed. So that will be much interesting if ever we can have such. I think many companies can be interested because we're doing a lot of riggings in power stations and manufacturing companies.
Exactly, 100%. We can definitely build an infrastructure to detect an object that's going to fall. And I've also seen a very interesting use case for detecting objects that have fallen. This particular algorithm was implemented, I think it was on an ice skating ring. And we had there was a camera overlooking the ice skating ring. And the algorithm detected whether someone had fallen on that ice skating ring. And then the operators would be able to go and carry out the necessary steps. So that was detecting whether something had fallen already, but there's no reason why we can't take that one step back and try and prevent that fall before it even happens. That would be a very interesting use case of this.
All right, thank you.
Okay, there's another question. Kuzwayo?
Hi, am I audible?
Yes, you are. We can hear you.
Okay. No, great presentation. My question was with regards to you spoke about pre-trained models, but with pre-trained models, you said they would train for a specific case, and you talked about how you can automate training data. Because the process of training data, you can either do it manually, but you said there's a way to automate it in MATLAB.
Yes.
Does it work better? And did you say you covered it in a previous what do we call it, seminar?
So the process of automating the labeling process is what we covered in this webinar. So what we did is we had a pre-trained network, or let's take a step back. Let me explain the workflow again, because it can be quite subtle, and it's a very powerful concept. We would take 50 images, for example, and we would manually label those 50 images. So we would sit there and we would draw boxes around the object in that image, and we would train a network. Now, obviously, that network won't be particularly accurate because it's only seen 50 images. We need many, many more, northwards of 500. But we can take that badly trained network and we can pass additional images to that, and we can use that network to generate training labels for those new images. So now we have a data set that includes even more images. Now I can train a second network on that bigger data set, and that second network will now be more accurate. And I can reiterate, I can use that second network to generate more labels on more images until I've built up a very large data set. And then I can train a final network on all the images, and that final network will hopefully be a lot more accurate. So essentially, you are using these badly trained networks, or not badly trained, but they have been well trained, but they might not be so accurate. You are using those networks to generate additional training data to train one final network, which will be a lot more accurate. And that just cuts down that training time.
Okay, now I see it. I see it now that you explained it that way. Thank you.
Sure, no problem. I think there's another question from Andy Sunny.
Oh, cool. Great presentation. But I have can't seem to understand why you so sure that given the fact you use a badly trained model, let's say you have 5 models, the 4 models which will help you generate data from a badly trained model does not necessarily mean that the last one will give you the right accuracy that you desire, given the fact that the data that was generated is already biased because of the bad models that you had used to generate the data with.
So that's an excellent question. And perhaps we can take a step back. We've discussed how this is automating the process. I think we can edit that term and call it semi-automating. Because what we're going to do, we're going to use those networks, those first networks, to train or label, automate the process. And then we can go back and we can make minor additions to it, as we did in that smoke video, where I lifted those boxes up slightly and moved them across. So that's why I'm calling it semi-automating. We're not going to purely rely on the labels that were generated. We will then go back and we will manually adjust them to perfectly fit the object, but at least I don't need to do that from scratch. And there will be some images where it's perfect and I can just simply skip over those images because it has been perfectly labeled. So again, it's semi-automated. You're right. If we had to just leave it up to its own devices and use those labels as is, then it will be biased 100%. But we are going to go back and we will manually alter them slightly. We will alter the labels which weren't particularly accurate, make them accurate ourselves. And there will be certain images we won't even need to do that. That is why it's semi-automated, not fully automated. And that will drastically cut down on training time because, as I mentioned before, there will be images where those badly trained networks did it perfectly. And again, I just need to alter that term badly trained networks. If they've seen 50 to 100 images, they won't necessarily be badly trained. They just won't be as accurate as we want them to be. So it's a very good question. And just to clarify, it's a semi-automated process.
Thank you.
All right, any other questions? Just remember, you can always pop me an email. My email address was on the presentation. We can engage in this topic. I think there's so much potential, so many interesting concepts. We want to hear from you. We want to hear about your use cases. If you've got any video footage or any other data, we want to hear from you and we can see how we can tailor-make these algorithms to your particular use case.